This is problem number 23 from our optimization homework, and it says what point on y equals 1 minus x squared is closest to 1, 1? So one of the first things I want to point out is the picture I drew in my solutions was wrong because I drew x squared minus 1, and this is 1 minus x squared. So this is correct, okay? My solution was correct in my homework. I just drew the wrong picture because I was tired when I was doing it. Okay, so here it is. Here's my parabola. It's opening down. Here's the point. And basically what we want to know, what point here is closest. Okay, so this is definitely the distance formula. So the distance formula is the difference in the y's plus the difference in the x's. And you could do it in any order, okay? It doesn't really matter. You just want it subtracting and squared and plus. Okay, so what are my y values? Well, one y value is, so this, we'll call this, how did I do it in my solutions? I guess it doesn't really matter. We'll call this point right here that we're looking for x comma y. Okay, so this will be my x2, y2, and this will be my x1, y1. Okay, but you could honestly flip it. Okay, so what I'm going to have is the difference in the y's are y, so the y here, minus 1 squared, plus x minus 1 squared. Okay, now, this is what I want to optimize, but in order to optimize it, I need to have it all in one variable. So this is where this piece becomes important. Because we're not just talking about any point floating in the xy plane. We're talking about a point that's on 1 minus x squared. So I'm going to plug in 1 minus x squared. All right, and if I go ahead now and clean this up, I'm going to get x to the 4th, because 1 minus 1 is x squared. X squared squared is x to the 4th. And then over here, I'm going to get, if I FOIL this out, x squared minus 2x plus 1. All right, that's what I want to optimize. Okay, here is the sad truth. We actually can't do this ourselves by hand. So you can go through the steps of finding this derivative, but it turns out that the derivative that you get, you cannot solve analytically. You still would have to use a computer, an online graphing tool, and all that good stuff. So for number 23, how we're going to solve this is we're actually just going to use DESMOS now. And we're going to graph this function. And we're going to see where does it have a min. And what we're going to see is that where this function has a min is at x equals 0.59. Okay, now, super important. We actually just want the x value here. And the reason why we just want the x value here for where we have a min is because if you give me the y value, it's the y value of the distance formula, not the y value that we're talking about up here. So we actually have to be a little bit careful. So the y value you get from DESMOS is actually d, the distance, okay? So in order to actually get the y coordinate of this, we need to plug it into this equation so it lives on the parabola. Okay, so if I take this min of 0.59 and plug it into this equation, what I'm going to get is 0.6519. All right, so the point that is closest to my 0.11 that lives on this parabola is the point 0.59, comma 0.6519. Okay, so again, in my solutions, my answer is correct in my solutions, but my picture, I drew the wrong parabola. So this is the parabola you actually want for number 23. I just was having a strange day. And one more time, we can find this derivative, but we actually can't solve it analytically ourselves. So since that happens, we can just graph this original distance function, find the min, and I just want the x value of that min, and then plug it back into our parabola to get the y value. All right, so there's our answer to number 23.